This paper is on toxic gas emissions from plywood fires, and it's one of the series on toxic gas emission from building materials. There are currently no requirement to measure toxic gas emissions from building materials other than smoke obscuration, and yet around 60% of deaths in fires are influenced by toxic gas emissions, which may kill people directly, or more importantly, through the irritant gases, prevent or delay means of escape. We're looking at 4 construction plywoods investigated using a freely ventilated cone calorimeter with raw gas sampling. And we're using 35 kilowatts per meter squared with free ventilation. This is the properties of the 4 plywoods, and one of the key things that was different is the glues that are used in the manufacture of the plywood give you a fuel-bound nitrogen content that you can see is extremely variable. Plywood B has nearly 6.5%. The light coloured plywood here, LPW, has 3.5%, and yet this plywood here is relatively low nitrogen. And we will see the HCN toxicity is not simply related to the nitrogen content, in that the time in a fire or the stage in a fire that the HCN from this is released is different. Its release we will see in B much later in the fire, but it's released very early here. So the HCN from this nitrogen is actually more dangerous than from this nitrogen. There are also differences in the stoichiometric air to fuel ratio from the 4 pyre. This is the cone calorimeter. We're not in this work using the air box, it's free ventilated, but on top of the cone we have put a chimney and we take a mean gas sample through heated sample lines to an FTI ore and then on to an oxygen analyzer. The gases from here entrain gases in the normal way, go to the rest of the cone, and we measure the total heat release using the usual oxygen consumption. Because we're measuring oxygen in the raw gases, we can get the heat release at this stage, and then we know how much additional heat release has occurred in the discharge from this fire. That this is equivalent to this stage burning is like inside a compartment, and this burning here is what you would see in the gases coming out the window of a compartment. We can also add particle size analysis to this, but we're not talking about this, those results here. So this is the primary heat release rate, and the first heat release here is the flaming combustion, and then you can see the charring combustion occurs later. The time of that is related to the thickness of the materials. You can see here. This heat release here we will see for plywood A is associated with a release of HCN, and plywood B, HCN. They are all got heat release in the flaming combustion, so you get a toxic peak here and then other toxicity later associated with these heat releases. This is the overall heat release related to those. By carbon balance we can get the equivalence ratio, and we can see even though this is a freely ventilated fire, the initial burning goes slightly richer than stoichiometric. All the later burning stages are also going rich, and in particular plywood B with a very high nitrogen content has a very rich burning up to an equivalence ratio of 1.8, and we'll see that that is where the HCN is concentrated. We get a high CO peak there and a high toxicity. whereas in this flaming stage, this always burns lean. So the flaming stage of this plywood is not as toxic, and we will see later that this later burning is where the key toxicity is. So this is our main emissions. The CO is related to those rich burning phases. That peak at 1.8 gives you the high peak here. This is the CO peak in the flaming burning, and you can see that the total hydrocarbons, when you add up all the hydrocarbons in the FTIR, follow. So the zones that give you CO also give you hydrocarbons. And some of those hydrocarbons are toxic. Benzene is the most important one, and you can see a big release of benzene, but least for the plywood with the highest nitrogen content, because that actually burns leanest. That releases its benzene in the peak here. Acrolein, this is extremely irritant, extremely toxic. All the plywoods are releasing acrolein early, which will affect means of escape. They are also all releasing formaldehyde early. These are the two most important irritant gases which will impair means of escape. Here's your HCN, and you'll see some of the plywoods release HCN early, but plywoods like B only release it predominantly in the char burning stage. So although it's a very high HCN peak, by the time that occurs, most people should have escaped the fire. And for impairment of escape, it is this peak that's most important. This is the total toxicity. So we've added all the toxic gases up, divided by the toxic limit, and added them up. And we're looking at two limits. The LC50, 50% of people die in 30 minutes. And again, you can see this peak early on, highly toxic. You're greater than 10. Does this mean that 50% of deaths will occur in 3 minutes? And this is a high toxicity for the material with the highest nitrogen content very late in the fire. Hopefully, most people would have escaped by then. And for each of these through the fire, you can see here that this is what are the most toxic. Early on, formaldehyde in terms of deaths. CO, important throughout the fire. All got this formaldehyde peak early on, which is going to give you an irritant gas impairing escape. We have been using the COSH 15-minute data as a way of looking at toxicity in terms of impairment of escape. It's very similar to the AEGL US data for AEGL2, which is called impairment of escape, and that's 10-minute exposure. So a huge impairment of escape peak in the flaming combustion phase, and then later peaks in the char burning phase. And you can see now that acrolein becomes much more important, both acrolein and formaldehyde, extremely strong early on, with more release, and benzene in there. CO, much less important. So these acidic and irritant gases are going to impair escape on all of these plywoods. We even have significant NO2, which affects lung function, so it gives you breathing difficulties in fires. So in conclusion, high concentrations of toxic gases that would impair escape were produced by all plywoods in the initial stage of the fire where escape is occurring in the fire. The nitrogen content is an indicator of high levels of HCN, but the stage in the fire that the HCN is mainly released is different for different plywoods, and we don't really understand the mechanism of that. Clearly, the way plywoods are manufactured and their composition affects their toxicity. Plywood B had the highest nitrogen content, but did not have the highest HCN in the flaming part, in the initial part of the fire. And finally, we believe that this modified cone calorimeter is a good technique with the FTIR for assessing toxic hazards in building materials. Thank you.